Hi, welcome! So in this video, we're continuing our discussion of solving trigonometric equations, and we're moving on to some next level examples. So this is building on from the previous video, and we're just adding in another step. So previously we had our steps here, we had steps 1 and 2, and we're going to add a step 0 that we sometimes need to do in order to set up the problem. So sometimes our examples that we're given, our equations, are not going to be written in the correct form, or they're going to be a little messy. And so our first step is we're going to need to rewrite them in the form where we have a trig function of an angle equals something. So we want to just isolate that trig function so that we can solve. So this is mostly like just more examples of what we've already done, but just with this extra step that we sometimes do in the beginning. We keep our next two steps where we find the first answers in the interval from 0 to 2 pi, so the first revolution, and we add the period of whatever our function is to our answers. Okay, so for our first example, let's solve the equation 2 sine of phi equals negative square root of 2 for all solutions. So we have here 2 times our trig function, and we're going to want to just isolate that trig, that sine function. So for our first step, we're starting with 2 sine of phi equals negative square root of 2, and we're going to divide both sides by 2. So this leaves us with sine of phi equals negative square root of 2 over 2. This is all step 0 is, it's just to simplify the equation before we start manipulating it. Now that we've isolated the sign on one side, we can use the inverse to get our first solution. So we're going to say that arcsine of negative square root of 2 over 2 equals phi. So I'm taking that statement I had written and then using the inverse to find one solution. I do this so that you can use a calculator if you really need to, but I'll also show you how to do it with a unit circle. Alright, so arcsine of negative square root 2 over 2, that input is a negative, that value, and so we're looking in either quadrants 1 or 4 for arcsine, and this means we're in quadrant 4. So that is our y value, and we see this at 7 pi over 4, which is really negative pi over 4 using the arcsine. So our first solution is phi equals negative pi over 4, or we could write it as 7 pi over 4. I like to use the positive angles, it just is more comfortable for me, so I'll use the 7 pi over 4 here. Then we can look at our unit circle to find the other solution. I see that at 5 pi over 4, there is also a sign value of negative square root of 2 over 2. So our second solution is phi equals 5 pi over 4. Now that we have these two solutions, you can imagine adding the period each time to get to the next solution. Or we could go backwards by subtracting the period. So we're going to take that period of our sine function and add it to each of the answers. The period of sine of phi, which is the equation we're working with, is 2 pi. So we'll take our answers and add 2 pi k, leaving us with phi equals 7 pi over 4 plus 2 pi k, or phi equals 5 pi over 4 plus 2 pi k. And this is where k is an integer, which we write with this k in z math statement here. Just as a reminder, we're basically adding 2 pi times k, so k is some number, we're adding just some multiple of that period to get to all of the possible solutions, and this way of writing represents an infinite number of solutions to this equation. So you could choose any value for k that's an integer, plug it in, and you'd get a new solution, and you can do this forever. So we can write our final statement as our answer to the question, which says the solutions to the equation 2 sine of phi equals negative square root of 2 are phi equals 7 pi over 4 plus 2 pi k, and phi equals 5 pi over 4 plus 2 pi k, and that's for k is an integer. And there we go. So we followed our steps, we started with our equation, we isolated the trig function, we used the unit circle or the inverse trig function to find our solutions, and then we added the period. So not too bad, we followed those same steps, and we're going to do that in all of these examples. Let's try it again on another example. So for this one, let's solve the equation cosine of x plus 5 equals 6 for all solutions. So I'm starting with my equation and I want to isolate the trig function for my step 0. So I'm going to subtract 5 from both sides to get the cosine by itself. And so when I do that, I get cosine of x equals 1, because 6 minus 5 is 1. Okay, so now we have a simpler equation to work with. It's this cosine of x equals 1, and we can move on to our first step. So step 1 has us find all of the solutions in the interval from 0 to 2 pi, so in that first rotation. And so here we can use the inverse. We can say that our cosine of 1 equals x. That's going to give us one of our solutions. Or we can pop up here the unit circle. So cosine is the x component, and I see that at 0 or 2 pi, I have 1 as the cosine or the x value. And so here, my x is equal to 0 or 2 pi as my solutions. So you could use 0 or 2 pi, or 4 pi, or 6 pi, or negative 2 pi. You get the idea, but we're just trying to get the first one in this interval, so I'm actually just going to use 0, since that's the first solution we see. And something interesting is happening here. This is actually the only solution in our first rotation. So there aren't any other places where we have a cosine value of 1, it's just this one place. So this is kind of a unique case. We go an additional 2 pi each time to get to those next answers, and this makes sense because our period of cosine is 2 pi. So this is what we're going to add to our solution. So we have 0 as our solution, and we'll add 2 pi k to it. Now, when we do this, we're just taking 0 plus 2 pi k, and that 0 doesn't do anything, so our solution is really just 2 pi k. All right, then we write our final answer. So the solutions to cosine of x plus 5 equals 6 are x equals 2 pi k, where k is an integer. And that's it. So we followed our steps, we isolated the trig function, we looked at the unit circle and found the locations, or you could use the inverse if you like, and then we added the period to that solution. All right, we're going to do one last example for this video. Let's solve the equation square root of 3 tangent of x plus 1 equals 0 for all solutions. So our first step is to isolate the tangent. So I'm going to first subtract 1 from both sides. So I'm getting square root of 3 tangent of x equals negative 1. And then I'm going to divide both sides by that square root of 3. So I get tangent of x equals negative 1 over square root of 3. And now we have an easier equation to solve. Our next step is to find the first solutions in our first revolution from 0 to 2 pi, and we can use the inverse to do so. So the inverse says that arctangent of negative 1 over square root of 3 equals x. Now for tangent, I think it's kind of hard to use the unit circle sometimes since it's not cosine or sine, and so I'll draw the reference triangle here that I know this goes with. You have lots of options for how you do this, so I'm just showing which one kind of makes sense to me in the moment, but just know that you have many options for all of these. So we have to go through our process for solving an inverse trig function. Arctangent is in quadrant 1 or 4. Because negative 1 over square root of 3 is negative, we're going to be in quadrant 4, and so I'm going to be having my triangle there in quadrant 4. Then tangent is opposite over adjacent, so I'm going to have negative 1 as my opposite and square root of 3 as my adjacent, and referring back to my reference triangles, this corresponds to the pi over 6 triangle, which I'll write as negative pi over 6 since we're in quadrant 4. You can confirm this on the unit circle. So looking at the unit circle, tangent is y over x, which if I look here at 11 pi over 6, which is negative pi over 6, I can check what happens when I do y over x. So y is negative 1/2, x is square root of 3 over 2, and when I multiply by the reciprocal, my 2's are canceling, and I'm getting negative 1 over square root of 3, which is what I was looking for. So my options for this first solution are negative pi over 6 or 11 pi over 6. I like using the positive version, so I'll use that 11 pi over 6. Now remember, with tangent, we only need one solution. So we could also do 5 pi over 6. This would output the same tangent value, but we only need one since it's only pi away, and so basically just whenever you were using the tangent, we just need the one solution. So now I can proceed to my final step, where I'm going to take the period of tangent and add it to my solution. So the period of tangent is pi, and so my solution is now x equals 11 pi over 6 plus pi times k. And this can go into my final solution statement. So the solutions to the equation square root of 3 times tangent of x plus 1 equals 0 are x equals 11 pi over 6 plus pi times k, where k is an integer. So all right, in this example we did the same process. We isolated the tangent function, we found the solutions in the first rotation, or from 0 to 2 pi, and then we added the period of tangent. In the next video, we will upgrade this a little bit and start looking at equations where the period is different, so the period's been manipulated, but for now, that's it for this video. Thanks so much for watching, and I will talk to you in the next one.